Hello everyone, I'm Lance Fernandes and I'm from Georgia Institute of Technology USA, and today I will present our work on channel-side interlayer engineering in laminated Fe-FETs, where we systematically investigate how channel-side interlayer material affect different ferroelectric NAND flash matrix such as memory window, retention and disturb for Fe NAND flash application. The purpose of this work is twofold. First, to systematically investigate the role of channel-side interlayer on the key Fe-FET NAND matrix, such as memory window, retention, and pass disturb, and understand how the different trap densities and different CIL material affect the Fe NAND performance. Second is to establish a trap-based physical framework linking the CIL material properties to memory window degradation and reliability behavior. I will first discuss the motivation and the executive summary, which will be followed by experimental results. And the experimental results will follow modeling, where we try to understand the trap charge density for different channel interior material and understand the memory window degradation. And finally, I will give the key insights from this work in conclusion. So to start with my motivation, ferroelectric material has been considered as a potential candidate for next generation NAND flash application as we further scale the NAND flash technology. So when we consider ferroelectric material for future NAND flash application for the vertical NAND process, there are certain design constraints that we need to adhere to. First, the ferroelectric thickness needs to be less than or equal to 20 nanometer, including the channel interlayer thickness, and the write voltage needs to be less than or equal to 15 volt. So considering these two design constraints, we need to ensure that the memory window, which is the difference between the two extreme state, is as large as possible to enable multi-bit capability. So how to get large memory window? So if we consider a standard Fe-FET where the Fe thickness is 19 nanometer, we get a memory window of roughly 2.4 volts. However, considering the same physical thickness of 19 nanometer, if we insert a dielectric material such as Al2O3, we see that there is a significant enhancement in the memory window performance, which is roughly 3 times. Therefore, insertion of a dielectric material in the ferroelectric oxide stack, keeping the physical thickness same, results in significant enhancement of memory window performance. So in this case, when the dielectric material is inserted between the two ferroelectric stack, it is called as a laminated Fe-FET. So most of the previous work focused on gate stack engineering in this red region which I have highlighted, where many previous work considered different dielectric materials and its location, such as at the center or at the top side, as the tuning knob to understand and improve the Fe NAND performance and Fe NAND reliability. So most of the work is focused in this red region, and the channel interlayer has not yet been systematically investigated from a reliability perspective, and the effect of different channel interlayer materials on Fe NAND performance has not yet been investigated. Moreover, channel interlayer is very important for NAND performance. So a recent work in VLSI 2025 by Micron showed that channel interlayer is actually important to increase or enhance the ISPP slope and the memory window performance compared to the case or device where there is no channel interlayer. This shows that channel interlayer is actually essential for Fe NAND performance, and it is important to understand how channel interlayer affect the trap based reliability of Fe NAND. So the highlights of this work is as follows. This is the executive summary. In this work, we systematically investigate pure oxide channel interlayer material starting from low K SiO2 to Al2O3 to high K HFO2 on Fe NAND performance, considering laminated Fe-FET. So we see that as we go from SiO2 to HFO to CIL, the dielectric constant increases, which reduces the EOT. but at the same time, it also increases the trap density as we go from SiO2 to HFO2. So this has adverse effect on memory window retention and disturb performance. So overall, this work gives insight into role of channels and interlayer traps on memory window retention and disturb performance. The spider plot shown here compares the key Fe NAND matrix for different channel interlayer material, and as we can see from the spider plot, SiO2 CIL delivers superior performance followed by Al2O3 and HFO2. Before I go into the details, I would like to show the TEM images of the channel interlayer and the gate stack. So we did a focused TEM imaging, and we confirmed the thickness of each channel interlayer to be 1.5 nanometer, including the native oxide thickness as well. And we also did the TEM imaging of the gate stack, which confirmed the thickness of the individual ferroelectric and dielectric layer to be 8 nanometer and 3 nanometer respectively. Now, to calculate the EOT and the dielectric constant, we did split CV measurement. The connection scheme for split CV is shown here, where we short the source and the drain, and the CV measurement is shown over here. So as we see, when we go from SiO2 CIL to HFO2 CIL, the oxide capacitance increases, and we calculated the EOT value, and the EOT value tends to decrease from 5.7 nanometer to 4.7 nanometer as we go from SiO2 to HFO2 CIL. We also back calculated the dielectric constant for the channel interlayer, and we can see that the SiO2 channel interlayer, the dielectric constant is the lowest, and as we go from SiO2 to Al2O3 to HFO2, the dielectric constant of the interlayer tends to increase. So overall, we understand that the EOT decreases and the dielectric constant increases as we go of the dielectric constant of the channel interlayer increases as we go from SiO2 to HFO2 CIL material. Moreover, we also did polarization versus voltage measurement for the Fe-FET, where we again short the source and the drain, and we observe that the polarization versus voltage curves are nearly identical for all the CIL material. Therefore, we conclude that there is no intrinsic degradation or change in the ferroelectric properties of the Fe oxide stack, and thus any performance differences that arise that we will see forward will primarily because of the CIL traps and not because of the change in the ferroelectric properties, because the ferroelectric properties tend to remain nearly identical regardless of the channel interlayer material that is used. Now let us try to understand the NAND performance matrix individually. We will start with memory window first. So to understand the memory window performance, we used pulsed IV measurement, which is shown here, where we apply a program pulse followed by a read IV and erase pulse followed by a read IV to get the device's VTH. So as we see in the IV plot, the program state and the erased state is shown for all the CIL material. And as we transition from SiO2 CIL to HFO2 CIL, the programmed and erased IV tend to degrade. To further quantify this, we did multiple measurements and we extract the device VTH as well. So we plot the erase and the program VTH for SiO2, Al2O3 and HFO2 channel interlayer, and we see that the erase and the program VTH degrades as we go from SiO2 to HFO2 channel interlayer. And overall, this degradation in the device VTH leads to a 15% reduction in memory window for HFO2 CIL case compared to SiO2 CIL. So now why is the memory window degradation increasing as we go from SiO2 to HFO2? To understand this, we need to understand that the memory window degradation primarily comes from polarization screening. So when we apply a program or erase pulse, electrons or holes get trapped in the channel interlayer, and these electrons and hole they screen the ferroelectric polarization, which is shown here. And since the ferroelectric polarization is screened, the effective memory window is reduced. Now there is a channel interlayer material dependence as well, where if we used high K materials such as HFO2, it has higher trap densities, and higher trap densities leads to higher trap charges, and that leads to stronger polarization screening. which results in higher degradation or higher reduction in memory window performance. Thus, high K material have higher trap densities, which results in higher trap charges and a stronger polarization screening compared to SiO2 CIL. Now let us try to understand the retention performance for FE NAND. So the retention pulse scheme is shown here, where we either program or erase the device and extract the VTH after different retention time. We extract the VTH all from 1 millisecond all the way to 1000 second. The first half from 1 millisecond to 1 second, the memory window increases because of read after write delay. And the next half from 1 second to 1000 second, the memory window decreases because of depolarization field. Let us try to understand both of them individually. So considering the first half, between 1 millisecond and 1 second, the memory window increases because of the read after write delay, which is primarily observed in the erased VTH state. So to quantify the memory window gain, we computed the percent memory window gain between 1 millisecond to 1 second, and we see that the percent memory window gain is nearly identical regardless of the channel interlayer material that is used. What this suggests is that the fraction of the charges, trap charges that are getting detrapped, they are nearly identical regardless of the channel interlayer material used, which is evident from identical percent memory window gain. Now let us shift our focus to long time retention between 1 second to 1000 second. So what we observe here is that as we go from 1 second to 1000 second, the memory window tends to decrease. So to quantify the memory window decrease, we plot percent memory window loss, and we see that the memory window loss increases as we go from SiO2 to HFO2 CIL. So now there is a material dependency as well, where as we go from low trap CIL material to high trap CIL material, the memory window loss increases. So we can say that the memory window loss is related to trap density, where higher trap density leads to higher percent memory window loss, which we believe or we hypothesize is primarily because of higher depolarization field compared to low K SiO2 CIL material. Now let us understand the pass disturb performance in FE NAND. So pass disturb is essential. It is essential to understand the pass disturb performance in FE NAND. If we have to read the selected cell, we need to apply pass voltage to the unselected cell in the NAND string. So when we apply pass voltage, we need to ensure that the stored state is not disturbed in the unselected cell. So the pass voltage should ideally not disturb the stored state. So to estimate the pass disturb in the unselected cell, we use the following pulse scheme. We either program the device or erase the device, and we apply pass disturb cycles and extract the VTH as a function of pass disturb cycle to estimate how the VTH shift or evolves after repetitive application of pass disturb cycles. So the pass disturb pulse width is 50 microseconds for each cycle, and the magnitude of the pass voltage that we choose is the erase VTH plus 1 volt, which is 5 volt in this case. So let us start with the low VTH pass disturb or the programmed VTH pass disturb. So when we program the device and apply pass disturb cycles, the device VTH tends to increase as the number of cycles increase. So the increase in the device VTH is consistent for all the CIL materials, and this increase is primarily due to electron trapping in the channel interlayer material. However, this effect is much more stronger in HFO2 CIL compared to SiO2 CIL. The reason for this effect to be strong is because of presence of higher trap density, which results in higher or stronger electron trapping compared to SiO2 CIL, which has lower trap charges or trap density compared to HFO2 CIL. This suggests that if the CIL material has higher trap density or higher trap charges, that will result in higher electron trapping, which will increase the low VTH pass disturb. Now, if we go to the array state or high VTH pass disturb, there are two competing disturb mechanisms in high VTH state. The first is the electron trapping, which tends to increase the device VTH, which we also saw previously. And the second is the ferroelectric back switching, where in the erase state, repetitive application of positive pass disturb cycle tend to switch the ferroelectric material, which can reduce the device's VTH. So when the pass voltage is 5 volt, in high K CIL, we can see that the device VTH is increasing after repetitive application of disturb cycles. This suggests that the dominant disturb mechanism in high K CIL is electron trapping. However, if we see the SiO2 CIL, which is the black curve, after 1000 cycle, the device's VTH tends to reduce, which is different from the high K CIL. This suggests that the dominant switching mechanism in SiO2 CIL is ferroelectric back switching, which is observed after 1000 cycles. To further confirm this dominant disturb mechanisms, we apply a even higher pass voltage of 7 volt, and we see that in SiO2 CIL, which is the black curve, the device's VTH tends to reduce after repetitive application of disturb cycle, which suggests that ferroelectric back switching is the dominant disturb mechanism. However, in high K CIL, which is Al2O3 and HFO2, the red and the blue curve, the device VTH initially reduces, but after 100 cycle, the device VTH tends to increase, or the device VTH becomes stable even after repetitive application of pass disturb cycle. This suggests that initially the dominant mechanism is ferroelectric back switching, but after 100 cycle, the ferroelectric back switching is still there, but the dominant disturb mechanism switches to electron trapping from ferroelectric back switching. Now let us try to understand the effect of traps in the channel interlayer on memory window performance from a modeling perspective. So to model the CIL traps and memory window performance, we did 2D Centaurus TCAD modeling, and we used this memory window equation to model the memory window enhancement. QIT prime is the interface trap charge density at the ferroelectric dielectric interface, and QIT is the trap charge density in the channel interlayer material. This QIT prime, which is the ferroelectric dielectric trap charge density, is responsible for memory window enhancement, and detailed work to understand how they enhance the memory window has been done in our previous work, which is shown here. In this work, we will primarily try to understand how the channel interlayer trap affect the memory window performance. So these are the different parameters that we used for modeling the memory window performance, and there are certain assumptions that we have made. First is the interface assumption. The QIT prime, which is the interface trap density responsible for memory window enhancement, they are assumed to be equal at both the interfaces. Moreover, in practical scenario, the interface traps in the CIL material are spatially distributed, but to simplify the modeling, we assume that the trap charges that are spatially distributed are lumped into an equivalent trap charge density, which is QIT. So here we have plotted trap density with respect to trap charge density, and as we can see, as we increase the trap density, the trap charge density also increases, and as the trap charge density increases, the polarization screening effect increases, that monotonically reduces the memory window as the trap density increases. One important observation here is that as we go from low K to high K CIL, the memory window reduction slope also increases. What it means is that for a similar or equal trap density, the memory window reduction in high K CIL is much more stronger compared to low K CIL material. To further understand this, we have plotted memory window shrink, which is the difference in memory window without any trap charges in the CIL minus the memory window with trap charges at a specific trap density. So as we see here, as we increase the trap density, the memory window reduction or the memory window shrink increases for all the CIL materials. However, for the same trap density, SiO2 has the lowest memory window shrink, and HFO2 has the highest memory window shrink even for the same trap density. So the physical origin for this is because higher K material enhances the electrostatic coupling of the trap charge to the channel. So the trap charges are strongly coupled to the channel, and it increases the polarization screening effect. Therefore, even if the trap density is same, the memory window shrink or the memory window reduction for high K CIL is more compared to low K CIL. Further, we calibrated the experimental results and estimated the electric field. So we see that SiO2 CIL has the highest electric field in programmed and erased state with the lowest trap charge density, whereas HFO2 has the highest trap charge density but the lowest electric field across the IL in programmed and erased state. So we saw previously that SiO2 CIL delivers superior reliability performance. This suggests that instead of electric field across the IL, trap charge density is the dominant limiter in the reliability and memory window performance. Moreover, we also calibrated and estimated the memory window for SiO2, Al2O3 and HFO2, and we show that the memory window closely matches to the experimental results, and which is shown by the dark bar plots here, and the light bar plots show the memory window without the presence of trap charges. So in a hypothetical limit, if we assume a trap free high K CIL, it will yield the highest memory window compared to low K CIL, which is shown by the light bar plots here. This suggests that if we are able to achieve ultra low or significantly low trap charges in the channel interlayer material, in high K channel interlayer material, that will result in highest memory window performance compared to low K SiO2 material. So overall, to conclude the work, this work systematically investigated SiO2, Al2O3 and HFO2 channel interlayer material in laminated gate stack for Fe NAND application. And we see that channel interlayer material critically govern the Fe NAND performance, impacting memory window, retention and pass disturb through trap mediated electrostatic effects. And the overall summary for different Fe NAND performance matrix for SiO2, Al2O3 and HFO2 is shown here. And overall it can be seen that SiO2 delivers superior reliability performance compared to Al2O3 and HFO2. Further, high K CIL reduces the EOT, but it increases the trap density as we saw previously. And trap density rather than permittivity alone is identified as a dominant limiter of memory window. What it means is that even if the electric field across the CIL is low, but if the trap density is higher, then trap density will dominate the reliability of Fe NAND. If we are able to achieve a high K CIL with ultra low trap by performing trap engineering techniques or using trap engineering techniques, then that represents a promising path to enable low EOT, high memory window and high reliability Fe NAND operation. So future directions to enable high K CIL with low trap includes interlayer nitridation to passivate the trap, or using oxynitride based CIL material, which can enable low EOT with high K CIL, and it can also enable low trap to enable high memory window and high reliability for FE NAND application. Finally, I would like to thank the sponsors Semiconductor Research Corporation, Supreme, and Samsung Electronics for sponsoring this work. And with this, I would like to conclude my talk. Thank you very much.